So let's get started. I would like to welcome everyone to our product showcase presentation, More Than an R-Value, Acoustics in Commercial Buildings, sponsored and presented by ROCKWOOL. I would like to thank ROCKWOOL for being a longtime sponsor of New York Passive House, which makes events such as today possible and advances the passive house industry here in New York. It's my pleasure to introduce Jose Sosa, who is a New York Passive House volunteer, and will introduce today's speaker.
Thank you, Andreas. Hello, everyone. Jose Sosa here. It is our pleasure to welcome Todd Kimmel, who is a certified passive house designer and is the New York City architectural manager for ROCKWOOL and a New York Passive House board member. Todd has over 18 years of technical experience working on building enclosures and facade systems, and is an outstanding expert and resource to all our professionals. With that, I leave the virtual space to Todd and the ROCKWOOL team.
Great. Thank you, Jose, and thank you, everybody, for attending today's program and for being a member of New York Passive House. Just to further introduce our team. So this is me, of course, as Jose mentioned, and Andreas. I'm affiliated with New York Passive House as a board member. I'm also an ambassador for the Building Energy Exchange here in New York City. If you're familiar with them or not, they've got a lot of great education and programs as well. And I currently serve as the chairperson for the Rain Screen Association in North America, which is a new industry association to really promote high performance rain screen assemblies in both our commercial and residential marketplace. So there's some good information all around. I don't have images of the individuals from ROCKWOOL that are here supporting us as well, but John Ram, who's the architectural manager for us in the Texas region and managing the western half of the United States, is here as well. I asked him to sit in on this because he's had a lot of experience presenting our acoustics presentation. So if you guys have questions during the program itself, if you want to type them into the chat box, as Jose mentioned, John would be there to address those more specifically, and he can also catch me if I say something incorrect. So we'll see how that goes as well. And then Joseph Donnelly is our roofing manager as well, and you'll see that acoustics really pops up more and more these days with building enclosure and the tie to passive house, and that would relate to our roofing assemblies as well as our exterior wall assemblies. So I thought it would be good to have him here as well. And so quickly before we jump in, I think many of you are familiar with ROCKWOOL. If not, we're called ROCKWOOL for a reason. So we do use stone as the basis of materials in the thermal and acoustic insulation that we manufacture. It's a very resilient material. There's a lot of great properties around stone that can help buildings and kind of promote health and well-being within our structures. So we're going to spend time after this presentation, following the Q&A session, connecting the dots with ROCKWOOL and certainly acoustics and passive house. But just the low-hanging fruit, I mean, non-combustibility is a big reason why people are considering stone wool insulation for their buildings. We'll get into discussions around thermal stability, water repellency, vapor permeance, right, as we're reducing heat flow across our enclosures with high-performance facades, right? We used to build air leaky and uninsulated, which meant if you put a fireplace on, it would dry out the walls. It's harder to do that these days in these assemblies, so we want to think about natural diffusion through these assemblies to dry them out. And so stone wool can really help contribute to that durability and resilience by being vapor open. Sound absorbency, we're going to talk a lot about as we go, so that's another big quality. And so we do promote the 7 strengths of stone, which you can see here. All the categories of products that are manufactured by ROCKWOOL as a whole align with one or typically more of these 7 strengths, from fire resilience to thermal properties to acoustic capabilities, robustness, aesthetics, water properties, and circularity. We do have groups that are not specifically for commercial insulation. So for those people that are unaware, we have a whole division called ROCKFON that makes acoustic ceiling tiles. We have a division in Europe that makes actually facade panels out of stone fibers called ROCKPanel. We have a group here in North America called Grodan, which actually uses hydrophilic binder to create growing mediums for the horticulture industry, the hydroponics industry, which has grown so much. And so we've seen a lot of growth in that capacity as well. So there's more divisions of what we do. when it comes to buildings, we're not just a bat insulation. I think many of you are familiar with our exterior grade products, but we do a lot around continuous insulation, around low slope roofs, around below grade insulation, curtain walls, etc. So a lot of things that we get involved with, and we'll be happy to explore that more at the end of today's program. So this is an AI ACU, so certainly make sure you get your information into New York Passive House to get a full credit here. And so this is more than an R value, kind of discussion around acoustics. So we will give an overview of stone wool insulation, how it's made, the kind of connection to the passive house world and high performance, low energy, and then really diving into acoustics as being one of the health benefits, certainly a passive house, and how a fibrous insulation like stone wool can improve that. So we'll give you an introduction to sound in general. We'll talk about some of the codes that are out there for both STC and OITC requirements. And then we'll get into specific assemblies around walls, exterior walls and roofs, right? Kind of connecting all of those dots. And so to take it back a few steps, we'll define mineral wool and stone wool in general, right? So people that are new to the space or have never asked the question. So the term mineral fiber is a generic term that's the overarching category for a number of products that are fibrous inorganic substances. And so underneath that, you've got three groups that it can be classified. So one, as we know very well, is fiberglass, right? So that is a mineral fiber in that category. Commonly, we'll see that used as bat insulation in walls, but it can be used for other applications for sure. Then you have what's called mineral wools. And under mineral wool, you have two specific subcategories, one being stone wool and one being slag wool. And so mineral wool is made up a combination of natural stone, typically volcanic stone, and slag. And slag is a byproduct of iron ore. So when you're producing steel, you get this byproduct, which contributes to the recycled content of a mineral wool. And so if you have a higher percentage of stone than slag, then you'd be considered a stone wool. If you have a higher percentage of slag versus stone, you'd be considered a slag wool. And so those are the two differences there. And then last but not least, you have refractory ceramic fibers. These are also mineral fibers, but they're used for more high temperature applications, more industrial applications. You typically don't see them used in buildings. And so when we talk about manufacturing stone wool, again, it's the two primary ingredients, basalt and slag. You are heating them up to extremely high temperatures, and then as they melt, that melt is spun into fibers. And then depending on how closely connected those fibers are, you can form them into either low density bats or into more high density boards, right? And that's going to kind of dictate the types of applications that you're using. And so I mentioned this already before we began, but just to reiterate some of the benefits of stone wool in the built environment. Non-combustibility is big, right? So stone wool can be heat resistant all the way up to 1,000 degrees Celsius, right? Its melting point is at 2150 degrees Fahrenheit. There's no smoke development. There's no toxic smoke. There's no flame spread. And so, when we talk about protection of occupants, people, contents of fire safety professionals, and you look at hourly rated walls or NFPA 285 compliant walls, it's no wonder that stone wool is typically top of mind when you're starting to design with fire in mind. Some other things that are also important for durability and robustness of our buildings, and why stone wool might connect the dots with passive house quite well, is that it is a long-term performing product, right? The R value will last quite some time. It will also, as an insulation that captures its R value from trapped air, there's no specific off-gassing, right? So you're not going to lose R value over time, which is what you will see with some of the rigid foams, particularly polyiso and XPS, which both use blowing agents, which will off-gas for, and that's not great for a number of reasons, but it will reduce R value over time. And then as temperatures drop outside, stone wool, like many insulations, will improve its R value as opposed to certain products like polyiso, which will tend to lose R value as temperatures decrease outside. We're going to talk a lot about acoustics, but stone wool products can create quiet spaces, particularly where they're needed most. So when we talk about school environments where speech intelligibility is so critical, having acoustically high-performing materials can really help the health and well-being of occupants. And yeah, so when we look at the future, right, over time, stone wool is able to maintain its R value for decades. In fact, we still see peak performance after 55 years of use with products. We have products in buildings for over 80 years, and they're still securing the R value that they did the day that they were made. So again, when we're building these buildings and we're expecting them to last a century, you want to use materials that can really continue to perform at the level that you would expect. There's no movement on these products so that they don't contribute as much to other materials as far as convective thermal loss, other types of issues. And so it just tends to be a very robust product. When we look at the big picture, I think many of us are aware of the impact of carbon emissions from our buildings. In urban environments like New York, it's not just 40% of the emissions from buildings, it's closer to 80 or 90%. As we know, passive house construction is the main component of trying to meet the city's 80 by 50 one city built to last plan. And you can see here this chart on the emissions or the energy use requirements of an average New York City building compared to a passive house. It's a no-brainer. With local law 97 and the Climate Mobilization Act upon us here in New York, passive house is seen as a really major pathway to reduce carbon emissions in our buildings, right, from the operational standpoint. And so when we look deeper at carbon emissions, we should know that operational carbon emissions is a big chunk of the building's impact. And as we start to build more high performance assemblies versus the standard typical building, the impact of embodied carbon, in terms of the carbon that's used to manufacture the products that we use and get those products to our sites, that ratio starts to increase, right? So we have a more awareness of embodied carbon in the materials that we use. And so as we look and assess different materials that are commonly used in commercial construction, this gives you an array of what that embodied carbon can look like. Mineral wool tends to be right in the middle of the pack there. Maybe not the optimum that you would see here on the bottom, but certainly not near the worst offenders of spray foams and extruded polystyrenes. But there's a lot of things that we need to consider beyond just embodied carbon, which mineral wool has a pretty good position on. And it's also important to note that when you look at mineral wools, embodied carbon can vary from material to material and density to density. And so, this chart is just kind of relaying different manufacturers of mineral wool insulation and their impact on global warming potential versus industry average. And so what I think is unique here is that some of the slag wools that are out there in the mineral wool fiber segment might have a good position on recycled content. But just because you have higher recycled content doesn't necessarily mean that you have a lowered embodied carbon. And so natural stone can oftentimes present more resilient materials, more robust materials than a slag wool, and it could also have a lower global warming potential. Also, mineral wools can contribute to saving 150 times the carbon emitted during its production. So again, because it can last a long time in our buildings and perform at optimum levels, it can actually do quite well. But we shouldn't also, we should also be thinking about bigger picture stuff even beyond carbon emissions. We're very focused on that right now, which is important. And EPDs can help kind of pave the way for knowledge for certain products. But we don't want to forget things that are critical as well, like ozone depletion, right? So certain products might have a lower embodied carbon statement, but they might have a higher ozone depletion issue with some of the VOCs and things that they're giving off in terms of the off-gassing to our environments, or certainly products that can combust and the impact that can have on ozone depletion. We do want to think about circularity and the ability to reuse materials at the end of, let's say, a project life cycle. And so stone wool insulation can really contribute well there. And then we can't forget health and safety, whether or not that's talking about non-combustibility and kind of fire performance, but also acoustics performance when we talk about health and well-being. And then last but not least, in order to maximize the benefits from a carbon standpoint of these products, we have to make sure that we're installing them in a manner that they can be most efficient, right? So we can't forget principles like passive house to reduce thermal bridging and ensure that you get the performance that you need. All right, so that was kind of an overview of stone wool. Now we're going to dive a little bit more into acoustics. But before we do that, as we're all aware, right, there's a passive house idea out there of kind of these benefits of using less energy, being more predictable. being healthier, more comfortable, more durable, and resilient. And so when we talk about acoustics and their intersection with Passive House, the two categories that we're focusing on here is being healthier and being more comfortable, right? So acoustics will play a role here and be a benefit or an attribute as we go to these higher performance assemblies. And when it comes to the methodology of Passive House, the two in particular, again, that are going to tie together with acoustics is certainly having insulation, additional insulation, and air tightness, right? So these two categories will have a direct correlation with acoustics in our building. And so we're going to start with what is sound, just on a very basic level, right? And so sound is essentially air pressure fluctuations that are coming from a source, a sound source, to our ears, right? And it's measured in decibels. It is not a linear correlation. It's a logarithmic scale. So when we look at decibels, for instance, if we hear a noise that's, let's say, at a 50 decibel level, in order to double that sound audibly to our ears, we would just need to move up 10 decibels, right? So it's not, again, you don't have to double from 50 decibels to 100 decibels. You're only upping the decibel level 10 to actually hear twice the amount of sound. Or to that point, if you took a 50 decibel sound and reduced it to 40 decibels, that would cut the audible sound in half to our ear, right? So just kind of understanding that this is a logarithmic impact. I was mentioning before the presentation, I had some audible slides here to kind of hear what that would look like. And unfortunately, the audio is not transferring. So I'm not able to share with you kind of what this perceived doubling would be and kind of how that would be impacted. But for those people who are interested, you can follow up with me afterwards and I can send you some good links on getting a sense of what that shift would be. But basically, a 1 decibel difference, you wouldn't be able to hear it. A 3 decibel difference, you can just barely hear that difference. And again, when you get to that 10 decibel level of difference, it would be either the physical doubling of sound, or if you were to reduce something 10 decibels, it would be the halving of that sound. And again, so sound is measured by decibels, just to give you a sense of how many decibels it takes, or kind of how to interpret the decibel levels. So what we would experience as a quiet room, let's say even a library room, you would be at a max decibel level of about 25. Normal conversation is at the 65 decibel level, a crying baby at the 75 decibel level. And then for us here in New York City, if we're 300 feet from an elevated subway track, that would be right up around the 90 decibel. And so when you look at acoustics and stone wool, there's really 5 categories or 5 properties and characteristics that can impact the sound within these materials, and that stone wool has some control over, right? Airflow resistance, dynamic stiffness, being able to provide some level of surface protection for the product, things like density, and as well as fiber diameter and orientation. And so airflow resistance, for instance, can be very impactful in reducing the sound through an assembly or through certain components. And what's nice about stone wool is that as materials get denser, it will have a higher airflow resistance. So you have the ability to control that airflow through these types of materials, and you have the ability to choose specific densities based on the category of products that are offered, right? So you have low density bats, all the way up to rigid boards, anywhere from 3 pounds per cubic foot up to 10 pounds per cubic foot. And so you can kind of play with that category. Dynamic stiffness and the rigidity can help reduce the structure-borne sound, right? So the stiffer you get with density can help with that. You can add surface protection, right? So you can add components or membranes onto the material itself that can optimize air tightness as well. The density, again, playing with that is important, and more specifically with stone wool fiber or stone wool insulation, you can modify the fiber diameters and the orientations again to help with sound reduction. So there's just a lot of components that you can play with within these materials. Specific to density and thickness, I see a couple of charts here on kind of how stone wool can create some level of noise reduction. And again, every frequency is going to be a little bit different. You can see here that lower density materials actually can perform better when you hear high frequency sounds, right? I'm sorry, low frequency sounds like basses or traffic outside, and as you get up in frequency, the higher density products start to perform just as well, or if not better. Absorption coefficient, right? So absorbing sound is a big part of this as well. And so the thicker you get, the more sound can be absorbed within the material. You will hit a point of diminishing returns, but for the most part, at the early onset of what you're specifying, the thicker you get, the better you'll be at that absorption. Sound isolation in buildings, right? So again, there's different ways or modes of transport with sound within buildings. So airborne sound is certainly a common one, and you'll develop assemblies to kind of control that. Structure-borne sound, like the tapping of a hammer or footsteps on a ceiling above, so that sound actually travels through the materials and can be audibly heard in the receiving room. And then what we can't forget is flanking sound. And so flanking sound, I would kind of correlate that to, when we look at nominal R values of insulation towards effective R values of insulation, or, thermal bridging per se. It's ways that sound can actually bypass our systems in constructed assemblies and kind of short circuit it so that sound makes it through, right? And that's kind of different ways that sound can get through. And so we can't forget flanking for sure, because you'll see the way we test sound, it doesn't really take flanking into account. So it's important when we look at assemblies on how to control that. And so we'll talk about that in general. The day-night average sound level DNL is what we use to kind of look at different regions or jurisdictions or even neighborhoods in terms of what sort of decibels we should be designing around, what sort of anticipated decibel level we plan to experience within a certain location. And so it is the average sound level over 24 hours for a specific region. But then when you look at the hours of 10 p.m. to 7 a.m., they'll add a 10 decibel penalty for that. And so really the reason why they do that is that in those evening hours where the ambient noise is quite low, standard noises sound a lot louder, right? Like a raccoon, kind of banging on a trash can, or, maybe a truck driving through down your street. In the evening time or late at night, it's just going to sound a lot more loud than it would during the day. And so that's kind of where you'll get that range. And so the sound transmission class, the STC rating, if you're familiar with it, is a rating that's calculated in accordance with ASTM E413. And it is, basically you have a receiving room and then you have a sound source, and it's measuring the amount of decibels that are stopped through that assembly, right? So in terms of the reduction of sound transmittance through that assembly. So the higher the number of an STC rating, the better the noise isolation is, right? So if you have an STC of 50, in theory, you're reducing the 50 decibels across that assembly. We're going to dive deeper into that because it's not specifically that simple. But really, it's only assessed or assigned to the specimens that are tested in a lab, right? So it doesn't oftentimes give you the real world data that you need. And you'll see that it is an average. And so as we look at different frequencies, that can certainly impact how an assembly will work. But it is measured over the frequency range of 125 to 4,000 hertz. And that's important to note here, just because when we look at a different rating called OITC, which is the outdoor indoor transmission class, it is essentially the same thing. However, it starts to measure sound at lower frequencies, right? So instead of starting at 125 hertz, it will actually calculate the ratings all the way down to 80 hertz. And so that's going to take into account things like airplanes, freeways, outdoor construction noise, things like that tend to produce lower frequency sounds that are really impactful for the indoor environment. And so you'll see, right? So, we're looking here on the right, our roof assembly, and as we're kind of doing the STC and the OITC ratings, you'll see that the sound source is above the roof, and obviously the receiver room is within the assembly itself. And so this assembly here is going to have an STC measured at 51 and an OITC measured at 39. Right, so it can perform better in theory, at the higher frequency, or the higher frequency sounds, whereas the lower frequency sounds, it's a little bit more below that. And just to again summarize, so OITC is typically used for exterior noise So you're going to see it applied to soundproofing windows, doors. We're seeing it more applied to exterior facade systems. And again, it's getting down to that 80 decibel, 80 hertz level in terms of the frequency ratings. And then SDC is going to be more for the common noises, things like TVs, music, speech, etc. And that's measured from 125 to 4,000 hertz. So how do we get to an SDC, right? And so, as I mentioned, you've got a sound source room and you've got a receiving room, and they're going to be creating sounds at different frequencies, and they'll measure the decibel transmission loss across that assembly. And then they're going to apply. So, and that's kind of the STL curve. So what you see here on the screen, the blue is what they're actually measuring at the different frequencies. But then they kind of correlate it to what's called the STC curve, which tries to give you your average. And so basically, you start to move that STC curve, overlay it on top of this blue curve, the STL curve. And first moment you have an 8 decibel difference is where that curve will then land. And so you can see here, once you've landed that STC curve on the STL graph, the STC rating will be taken at 500 hertz. So you go up from the x-axis up at the 500 hertz level where that hits the STC curve, and that's going to give you a 56 rating for STC. So again, it's not really telling you everything that's going on within this assembly at the different frequencies. It's giving you a very average look at this wall. So I say that because as we look at this curve, right, which is now, or these two STC curves, which is looking at this blue line, which is a 4-inch solid concrete wall, and then the other black line is a steel stud wall. You can see here that the blue line actually has an STC of 47. The black line has an STC of 48. But at those lower frequency sounds, you can see up to a 30 decibel difference that actually that concrete wall is actually performing much, much better at those lower frequencies than the steel stud wall would be. But the steel stud wall has a higher STC rating. So again, we really just need to make sure we understand what sort of sounds and frequencies we're designing for to ensure that those assemblies that we're using and constructing are actually going to conform to those walls. And so here's another example, and this just, these curves look very similar, right, in terms of how they range, but you'll see that the STCs are actually quite different, right? One STC is at 42, fairly average. The other is at a very below average rating of 32, and that's just because the 8 decibel difference in the first one, and the one that's 42, happens right at around the 126 frequency mark. And that the decibel difference for the black one happens, that gap is right at the beginning. And so because of that, we're looking at, a very low frequency shift that just makes these assemblies look quite different. So it's just misleading results due to the frequency cutoff. All right, so beyond just kind of wanting to make sure you're interpreting STCs and how that impacts assemblies correctly, I mentioned before the flanking paths and the impacts that these can have, right? So these are, different ways that sound can travel around an assembly, right? Certainly, one is kind of that STC and kind of how that, sound is traveling through. But there's different ways around those systems, whether or not that's through radiators, outside windows, or into other windows below the floor assemblies, above the floor assemblies, through piping. And so there is another rating called the apparent sound transmission class, which is much more about in situ. We do see ASTC actually starting to be referenced in Canadian code, but we don't see much of it yet here in North America. And so when we look at these flanking paths and recognize the impact that they can have on the acoustics of our assemblies, there are ways and solutions to design around them or to help prevent their impact, right? So you can see right in the upper left, right, there might be some flanking paths through walls, so we try to break those systems off as far as breaking the gypsum sheathing so that we don't see the flanking through the gypsum, but we have that stop and start at certain parts within our wall. We might add resilient channels within our assemblies to decouple the studs from the sheathing. Again, this helps to provide a more optimum solution and reduce those flanking paths. We're also probably fairly familiar with acoustical sealants, right? And so you can see here on the upper right, if you just have one bead of sealant, that may very well not be enough. And so you'll see, in these kind of more high performing acoustic assemblies, you're going to have multiple beads of sealant. You can see here on the right, we've got 5 beads of sealant, of acoustical sealant, to really help maximize the performance of that acoustically rated assembly. And there's different components in addition to resilient channels. There's new things that you can put on studs, on doors. So there's different ways to categorize and improve those assemblies. And then, of course, we're very familiar with air leakage through different types of electrical boxes within our wall assemblies. But sorry, when it comes to acoustics, we also want to make sure we're not doubling up boxes, right? That can also create air traffic and flanking paths through our walls. So trying to offset that as we go is another good design strategy to help improve. All right, so when we look at code, acoustics are popping up more and more these days. So you've got various ANSI standards that references, particularly for schools, where we again recognize the impact that noise and learning can have together, right? The cognitive performance of both children and adults can certainly be reduced by noise. So we want to kind of control that. So you'll see the higher STC requirements when it comes to these types of buildings. When we look at high performance standards such as LEED, you're now seeing the ability to contribute to LEED points, particularly in healthcare environments and schools, by improving your acoustic wall assembly. And so if you are in jurisdictions, and I don't think New York City has adopted the 2015 International Green Construction Code, I might very well be wrong there, but as you look at the Green Construction Code, there are specifics around types of buildings and their uses, and what the requirements are around STC ratings for these different uses, right? So you can see here, 60 STC for assemblies, or assembly uses, for factory uses, mercantile, residential. So we're starting to see an adoption of these higher performance requirements. Certainly around airports and in urban interfaces like New York City, if you're designing around JFK, there might be the adoption of the AICUZ, the Air Installation Compatibility Use Zone, where we start to see much more higher requirements for higher OITC rated assemblies. You'll see higher requirements for roof assemblies for sure in these jurisdictions. And as you get further and further away from airports, that requirement starts to diminish. Yeah, and so the green standard really applies to a variety of applications or locations. So buildings within 1,000 feet of expressways are going to be impacted here, as I mentioned, around airports, or more specifically in areas where you have day-night level average sound levels that exceed 65 decibels. So that's starting again to pop up in New York City. And we'll talk quickly about that, right? So, where should I be, or where should we be concerned about code requirements for noise pollution? Again, when you're close to infrastructure projects, when you're close to high traffic zones, airports, close to elevated trains, when you're in places again where you have a high average dBA. Also with mechanical rooms, right? We're also designing a lot of buildings with loud mechanical rooms, so that starts to kind of come into play. And then certainly under the ANSI S1260 standard for school rating systems. So jurisdictions that are really diving into a lot of this, I mean, California State Building Code now has very specific requirements around both STC, OITC. In New York City, you'll see here again where you start to exceed the 70 dBA is where you'll get some triggers on requirements for higher acoustic rated assembly. All right, so now we're going to look at specific walls and roofs and kind of how we look to design for acoustics and how we can start to make improvements, right? And so, when we look at a baseline for roof and wall assemblies, you can see, this is more standard types of assemblies that you'll see out there with different types of materials. The lower performing systems are identified here, on the left, but it's not just about acoustics, right? We're designing more than just acoustics. We're designing for R value as well. So we have noted here what the R values are for these assemblies at the bottom. So it's kind of balancing these things out. And so, when you look at, an all polyiso system here on the left, you'll have an STC of 31, an OITC of 25. You start to fill the flutes and maybe make slight improvements here. As you move to hybrid system solutions, where you actually have a stone wool insulation on top of your ISO board, now you start to see a steady increase in the STC in terms of how that sound absorption will work. And when you go to a full stone wool system solution, now we're starting to see some pretty good increases in the acoustic ratings. And again, it doesn't require much of a decibel difference to see a fairly large shift in the audible noise, right? So what I mentioned before, a 10 decibel difference is essentially having the noise that you'll hear through a system. So as you compare these assemblies, we are getting to some pretty good ratings. And last but not least, you also want to recognize the rainfall on these buildings, right? And so the decibel levels, the lower the decibel levels are, the lower the impact you'll have from the rain that are hitting these assemblies. When you look at walls, it's a similar story. So moving from, let's say, just an exterior insulated wall with XPS, even just moving from away to that to a bad insulation wall with mineral wool, you start to see some improvements there. When you see a combination of, let's say, mineral wool bat and polyiso on the outside, certainly doubling up that insulation can start to make some improvements, as we see here. And then moving to an all stone wool solution, again, is starting to give you the optimal acoustical solutions as we go along the line. When we get to high performance enclosures, when we start to look at things like Passive House, the numbers just get better. So again, here on the left is good, but as we can see here all the way on the right hand side, where we do now commonly see in metal frame construction, 6 inches of stone wool insulation on the outside. You can see even more than just 3 inches of stone wool, 4 or 5 inches. Now we're starting to see these kind of STCs going above 50, OITCs going above 35. And clearly, you're also getting to higher nominal and or effective R values. All right, so I'm going to throw a question out there. Feel free to answer in the chat as we look at these two assemblies. Do you guys want to make any guesses on which wall might have a better STC rating? I'll give you 10 seconds. All right, so for those of you who guessed the assembly on the right, unfortunately, you're incorrect. The one on the left actually has the highest STC rating. I didn't write the numbers down in front of me, but I think it's an STC of 58 versus 57 or 56 on the right. So they're fairly close. But the assembly on the left is doing a good job of decoupling. It's a double stud assembly, so that's a big deal in terms of how they separate that noise there. They're using specific sheeting that's meant for sound break. So despite the fact that you might see resilient channels on the right, it just wasn't the same. But with that in mind, the ratings were not that different, and the assembly on the right is a narrower assembly. It's probably a less costly assembly. So again, it's a matter of what is the code requiring and what are you trying to achieve and what are the uses of your building. And we can't forget what are the frequency sounds that you're also trying to control, because that may or may not have an impact on that STC rating. All right, so putting it all together. So from a design freedom standpoint, we want to remove all acoustic barriers, right? We want to develop high STC rated assemblies. I think when it comes to our roofs, it's great to be able to have open plenums and unique design opportunities, and to move all of that insulation and the acoustic requirements above the deck. And so when we do that, there's some really good opportunities with stone wool insulation to get to those higher ratings and give you more design freedom within the structure itself to have these open spaces. As we mentioned, for schools, it's really great from a learning and education standpoint to minimize the noise coming in from the outside or from adjacent classrooms, and to really focus in on what the teachers are saying. But not only that, when you talk about stone wool, also this occupant safety, we mentioned fire, and kind of just optimum performance overall, right? So there's a lot of considerations there that we need to have when you're designing around transit hubs and specific airports. It's really important to consider, obviously, fire safety, but also acoustics tends to be a big deal in these locations, particularly at those lower frequency sounds, which is where stone wool really provides some great value. All right, I got through that quicker than I thought. Hopefully it was digestible, but I think, Andreas, we can open up the channels for questions. I don't know if there were questions through the chat box as we went.
So maybe I take the first one. What are the energy requirements to create mineral wool, and can this be translated to CO2 emissions? And
So I don't have the data in front of me. I mean, we do have to heat product up. And so we have a great sustainability guide that we can share with you, as well as the EPD that might have some of that data. Basically, as I mentioned, the thermal insulation over its lifetime will save 150 times the amount of carbon that was emitted during its production. So that's a comparison, but I don't know the specifics on that. Not that we don't have the data, but I'd have to follow up with whoever's asking that to get them that information.
But I just dropped the link to ROCKWOOL's website that talks about our life cycle assessment and information to our EPD as well.
Okay, perfect. Thank you, John.
And I think in the same, there's a question by Suzanne as well. Can mineral wool be recycled?
Mineral has the capacity, to kind of have this cradle to cradle approach within circularity. As far as when that product is taken off a building, it can certainly, if it's in good shape, it can certainly be used on another structure. It can also be brought back to a production facility to be recycled and kind of remade into more mineral wool. So we do have programs that will do that in Europe, where our job sites are fairly close to our manufacturing facilities. Unfortunately, here in North America, we don't have that program set up just yet. And oftentimes, based on where we're producing these products, the carbon impact of getting them sent back to those production facilities will outweigh the benefits. So it does have the capacity to be recycled, and it can certainly be reused. So those are two great things that we can help promote.
Mm-hmm. So if you recycle, so in the future, hopefully that one has used rock wool or mineral wool, you would just basically recover that material and then ideally send it back to the rock wool.
You could put it back in the hopper of production, and it can be remade into new product.
So you don't have to melt it down again. It's just a question.
Well, so in that case, you would be melting it down again. But if it's in good shape, you can continue to use it, right? So it's a very stable R value. So it just depends on, so if you are pulling board product out of a building that that it's currently installed on, if it's still in good shape, then you can go ahead and use it on a new project. So there's no issue with that in terms of the loss. But as far as trying to take an old bat and then recycle it into a new product, it would go back into the hopper, but you wouldn't be using any virgin material in that way, shape, or form.
Thanks for the clarification. And there's a question by Andreas. He's asking, what about 4,000? What about higher frequencies than 4,000 hertz? So like a crying baby, or music which can reach much higher.
Oh, that's interesting. I think that the STC range includes that level of frequency. So I think, and maybe John would know that better than myself, but I think, or I guess maybe I don't know the question. So, I mean, those are captured within the STC ratings. And so you'd have to go back to that chart to see kind of how Stonewall addresses that. But that is captured within STC, right? So those ratings of frequency.
So I'll answer Andreas's question. I've done a little bit in the chat, but one of the things that the industry has to comply to is STC, because it is written into the code. What we try to kind of make aware to the design community is that there are sounds that happen outside of that STC range, and we should look at how systems perform. So an STC is that average number, but when we do an STC test or we look at the performance of these wall systems, we can look at sounds outside of that 4,000 range and say, how are they performing? So if we're designing a wall that we know is going to see a lot of high frequency noises, we want to make sure that the products that we're specifying and designing into those systems respond well at those sounds. So just because we might have a high STC number, it does not mean that that system is going to perform well at those areas. And we really want to assess how that system comes together outside of it. And one of the things that we look at is product performance and something called NRC, which is the noise reduction coefficient. That looks at how that product responds at that individual frequency. So we can test NRC values down to the 30 hertz range or all the way up to 16,000 hertz to see how a product responds at those levels. And then you can make adjustment on, is this product right for that application? So hopefully that answers two of the questions in there, talking about difference in products across spectrum of sounds as well.
That's great. Thanks, John.
And John, do you want to take on the next question as well? I see you answered a little bit in the chat box, the binder of the material.
Yes. So ROCKWOOL products do have do use a formaldehyde content in that binder. Some of the materials we do have non-formaldehyde based product as well, and all of ROCKWOOL products do go through testing. And when they go through our curing oven, a lot of the binder that is used is burned off. It actually emits very low levels of formaldehyde, so we can get Green Guard Gold and Green Guard certificates on a lot of our products that are used in applications where that would be a concern. The industry is obviously moving towards that, and ROCKWOOL is continuing to develop products that meet those industry standards that are there.
Yeah, and that includes LBC compliant, right? So we do have kind of the declare labels, and we can meet LBC requirements for both the BAT and the rigid products.
And there's a question here on structural panels. So ROCKWOOL does manufacture, or not manufacture non-structural panels themselves, but companies like Kingspan, Metalspan, or typical sandwich wall manufacturing panels can be produced with a ROCKWOOL core or a stone wool core. So that's something that they will purchase from us and then manufacture into those panels. So all of the leading sandwich wall panels, or kind of structural, non-structural panels that are on the market, do have the availability to use stone wool in their systems.
And even the insulated metal panels for aesthetics, like the Centria panels or things like that, will use stone wool for their non-combustible stone wool options.
And I think there's one last question, John. Maybe you want to take that on as well. Adam's question about the NRC.
Yeah, so Adam, you are probably right. I probably misspoke in saying that the NRC value is a single number, and we would look at the transmission loss coefficient. So thank you for that clarification. That transmission loss coefficient would be calculated to get the NRC value.
Well, I was gonna, before we close out, if people want to stick around, so I was just gonna connect the dots on ROCKWOOL a little bit with the acoustics, right? So that let people know, if you're not familiar with it, ROCKWOOL does manufacture, again, roofing products for low slope roof. We have a product called ROCKWOOL Multi-Fix that can be used wholly on a roof. It can be included in a hybrid assembly where you actually will cover a polyisocyanurate to protect the polyiso from the thermal shifts that could impact its performance. So you start to insulate the insulation, but it gives you additional fire protection. And then kind of a cover board that's inherent with the system itself, right? So the stone wool can be applied a dual density product once you get to certain levels of thicknesses, and so it tends to be a very good option there, and it can integrate with most membranes that can be applied directly over the surface of the material. Top Rock DD is also there as well, and so this I believe can do everything that Multi-Fix can do except for a self-adhered membrane. So that would be the only difference here. We got different products there. On the walls, we oftentimes see our ROCKWOOL cavity rock used. This is a semi-rigid board that would be used in, let's say, a rain screen assembly or a masonry wall. And so again, this is meant to interface with the environment. This is at about a 6-pound density, so a pretty optimum density from an acoustic performance as well as a thermal performance range. So this one of our more higher R value products at roughly 4.3 R per inch. We have boards as well, so the boards can be used on vertical walls, and these are more rigid than that semi-rigid cavity rock. So this is a product that can actually transfer the compressive strength of a cladding system through it. Right? So when we talk about light or medium weight claddings like fiber cement or porcelain or HPL or ACM, you can have an extrusion sit outboard of this product, and the only breach or thermal bridge that happens within this material itself would be the fasteners that are connecting those systems back to the structure. So it tends to be very beneficial for kind of these high performance. From the bat perspective, our AFB and AFB Evo are low density bats that are used primarily in partition walls in buildings. We have, again, a very good acoustical ratings here. John mentioned formaldehyde-free products. Our AFB Evo is the formaldehyde-free material that you would see used within these applications. Comfort Bat, also a low density product. This would be more specific to exterior stud walls as opposed to partition walls. So we published this one with an R value on it. And so this would be like for metal frame assemblies or wood frame assemblies on the outside of a wall. And it tends to partner very well with a semi-rigid or a rigid product on the outboard side, providing more continuous installation. And so we have some really good acoustic guides. So beyond what we presented here today, which we're more than willing to share a PDF of today's presentation, but we have some more specific guides and tools, even specific to the New York marketplace, in terms of what our assemblies are achieving from an STC and an OITC rated value. And that applies again both to roof assemblies as well as vertical wall assemblies. One last thing, and I think many of you are aware of this, and I'm gonna, some new content beyond what I'm presenting here now is ROCKWOOL offers complimentary building science services. So, you know, as you guys are working on your passive house buildings and you want to get a sense of dew point analysis or, you know, measure your effective R values specific to your assemblies and the climates that you're designing in, we can offer those services complimentary. We can provide full reports. We can get to you your effective R values or the U values of your assemblies as part of your submissions to DOB. So feel free to reach out to me and leverage this service. We do quite a bit of this work, and it's very useful and certainly at a no charge cost, very cost effective. But I was informed by our building science team that we are actually now starting to open up this service to acoustics as well. So if you guys need to analyze your assemblies for to calculate STC or OITC ratings, we are at a position where we can start doing that. So please feel free again to reach out to me if that's something that you'd like to pursue. This is my contact information again, so feel free to write it down, or certainly I'm sure Andreas can provide it as well.
I would like to thank everyone for joining, and I would like to thank Todd and the ROCKWOOL team for the fantastic presentation.
Thank you, everybody. Thank you, Andreas, and to New York Passive House for supporting this.